Okay, day 5 and 6, continuity and discontinuity. A function f is continuous at c if the limit of f of x as x approaches c equals f of c. If f is not continuous at c, then c is a point of discontinuity. Three-step definition of continuity. So this is very important. In order for f to be continuous at c, the following three conditions must hold true. F of c is defined, the limit of f of x as x approaches c exists, and those are equal. So the limit of f of x as x approaches c equals f of c. The following functions are continuous at every number in their domain: polynomial, rational, root functions, trigonometric functions, inverse trig functions, and exponential and logarithmic functions. Y equals f of x has a derivative f prime of c at x equals c, then it is continuous. So basically, if it has a derivative at a certain place, it's continuous. The converse, however, is not true. If it's continuous, does not mean it necessarily has a derivative. So example, at a sharp point or a vertical tangent is another place. So, for instance, an absolute value graph. So for example, oops. Okay, so cannot take derivative at x equals 0 because there's a sharp point. If we have y equals, let's say, cubic root of x, no derivative at x equals 0, and that's because there's a vertical tangent. So right there at 0, you cannot take the derivative. Removable discontinuity. Oh, I think this kind of looks backwards here. This is trying to say there's removable discontinuity at that place in the graph. Removable discontinuity occurs when there's a hole. So this graph here, there's a hole right there. So removable discontinuity at x equals 1. So it's kind of like if you plug the hole and then the graph would be continuous. That's what you would think of when you think of removable discontinuity, when there's a hole that you could plug and it would make the graph continuous. Jump discontinuity, it's exactly what it sounds like. There is a jump in the graph. If I were tracing this graph, I'd have to jump to continue tracing it. So I'd have to jump up here to continue on down. So that's jump discontinuity. So, this one has jump discontinuity at x equals 0. This one at x equals 1 has jump discontinuity. Jump discontinuity at x equals 1. Infinite discontinuity is basically, you would think of an asymptote. If there's an asymptote, then there is infinite discontinuity. List the domain, range, points of discontinuity, and their type. Okay, so for domain, a lot of times we go through thinking vertically. So this graph is going from 0 over to 1. There's no x values at 1. So soft bracket. Then from 1, okay, there's stuff at 3 to 5. So from 1 to 5. And then from 5 over to 7. So at 5, there's an asymptote. At 1, there's a hole. Now at 2, there's a hole, but then notice there's a closed point, and the same thing happens at 3. So there is an x value at 2 and at 3. Range, we go through horizontally. So if you kind of thought of putting like horizontal lines through the picture, we're hitting at 1 all the way up to infinity. So from 1 to infinity. Now we have removable discontinuity at, let's see, where do we have holes in the graph? X equals 1, x equals 2, right? So if we plugged those holes, it would be continuous. Notice at x equals 3, there's a hole, but if I plug it, it's not going to be continuous. That's because there's actually a jump in the graph. So we have jump discontinuity at x equals 3, and then we have infinite discontinuity at x equals 5. Okay, so given this piecewise function, they say A, does f of 0 exist? Now, we don't need to graph it to determine if f of 0 exists. We can just look for where is x 0. So this interval here has where x equals 0. So I would plug into this. So it'd be 0 minus 1 or negative 1. So yes, f of 0 exists and it's negative 1. They ask, does the limit of f of x as x approaches 0 exist? Well, when we talked about limits graphically, we said for a limit to exist, the limit from the left has to equal to the limit from the right. So I'd have to check, does the limit of f of x as x, or I would check, what is the limit of f of x as x approaches 0 from the left? Then what is the limit of f of x as x approaches 0 from the right? If those are not equal, then the limit does not exist. So let's see, from the left of 0 is this interval, right? So we would be plugging into this. So I would say 0 squared minus 1 is negative 1. 0 from the right is here. That's immediately to the right of 0. So we would use this, 0 minus 1, negative 1. So yes, limit of f of x as x approaches 0 equals negative 1, which means it does exist. Does the limit of f of x as x approach 0 equal f of 0? Well, that's asking basically, as my answer from part A and part B equal? Yes. Right? A was negative 1. The limit of f of x as x approaches 0 was negative 1. So what can I say about f at x equals 0? It's continuous. That is showing our three-part definition of continuity. F of 0 exists, so does the limit, or we could say it's defined, and then those are equal. So that means it's continuous. So for example 3, it says state find any points of discontinuity or state if the function is continuous. If it's discontinuous, state the type of discontinuity. Okay, with fractions, what you want to look at is first, does anything factor cancel? Because factor cancel means there's a hole in the graph. So when I look at the numerator, does not factor. So there's not going to be a hole in the graph. Now I look for where the fraction is undefined, where else it would be, if it has a hole, it'd be undefined at the hole. This does not have a hole, but we never want the denominator of a fraction to equal 0. So there is a vertical asymptote at x equals 1. That's what would make that fraction 0, which means there's a vertical asymptote. That is infinite discontinuity at x equals 1. That is the type. The next one, I can factor. I want multiplies to positive 15, adds to negative 8, which is negative 5, negative 3. But notice, I can't cancel. There's no common factor on top and bottom, so we still do not have a hole. But we have two vertical asymptotes here. We have a vertical asymptote at x equal 5 and at x equal 3, because those both make the denominator 0. So again, that's called infinite discontinuity at x equals 5 and at x equals 3. The next one, let's think about it. Is anything going to make x squared plus 8 equal to 0? That would be x squared equals negative 8, square root. X would be equal to plus or minus the square root of negative 8, which is imaginary, meaning there's nothing that's going to make it 0. So this is continuous. This is an absolute value graph. So, might look somewhat like this. So it's continuous. This is 3 cubic root of x. So this is a cubic root graph that's been vertically stretched. That's continuous. So we said root graphs were continuous. Absolute value graphs are continuous. This one I think we looked at once before. It looks like this. There is jump discontinuity at x equals 0. Now, let's say you didn't know what that graph looked like. You could just start putting in values. If I put in 0, it's undefined. If I put in 1, so let's see, if I put in 1 for x, I would have absolute value of 1 over 1, which would be 1 over 1, 1. If I put in 2, absolute value of 2 over 2, which is 2 over 2, 1. 3 would be 1. If I put in negative 1, I'm going to get negative 1. If I put in negative 2, I'm going to get negative 1, so on. You could just figure out a table of values. Okay, and for this one, we're going to factor. We always have to factor to see if anything's going to cancel. Okay, when I factor that, the x minus 6 cancel, which means I have a hole at x equals 6. I have a vertical asymptote at x equal negative 2. So it's removable discontinuity at x equals 6, and it's infinite discontinuity at x equal negative 2. Okay, they say define f of 1 in a way that extends that function to be continuous at x equals 1. All right, well then f of 1, in order to be continuous, it would have to equal the limit of the f of x as x approaches 1. Right? That's our three-part definition of continuity. The limit has to be equal to the actual y at that x value. So f of 1 is the y value when x is 1. So f of 1 would be the limit as x approaches 1. Now this is a good review of limits because we need to keep limit until we plug in. That's actually taking the limit. This is going to be our SOAP formula, right? A minus b, a squared plus ab plus b squared. That's our a cubed minus b cubed is a minus b, a squared plus ab plus b squared. On the bottom, difference of two perfect squares, x plus 1, x minus 1. So when we do a limit, we're going to factor, cancel, and then plug it in. So when I do the limit as x approaches 1 of this thing, that would be plugging 1 into that, which means then I can drop off limit once I plug in. So f of 1 would have to equal, what, 3 over 2. Adding the top, we get 3. Adding the bottom, we get 2. Okay, now they say what value should be assigned to a to make the function f of x continuous at x equal 3. Well, in order to be continuous, we know the limit has to exist. In order for the limit to exist, the limit from the left has to equal the limit from the right. So the limit of f of x as x approaches 3 from the left would have to equal the limit of f of x as x approaches 3 from the right. So let's see, 3 from the left, x is less than 3. This is to the left of 3, so it would be 3 squared minus 1. 9 minus 1 is 8. For this one, I'd have to plug 3 in for x here. So it would be 2a times 3, which would be 6a. A would be divided by 6, so 8/6 or 4/3. So we could say a would have to be 4/3. Find a and b so that f of x is continuous everywhere. This is the last one. So in order to be continuous everywhere, I have to make sure there's no jump in the graph at 2, and I have to make sure there's no jump in the graph at 4. That's where there could be, with a piecewise function, that's where there could be the places of discontinuity, wherever the interval changes. So I would have to do the limit of f of x as x approaches 2 from the left. I would have to see, make sure that that equals the limit of f of x as x approaches 2 from the right. So 2 from the left would be here. So I'd be doing 3 times 2 minus 2. 2 from the right, I'd be plugging in 2 to here. So it'd be a 2a plus b. Or I don't know if you need to see that. So it's a times 2 plus b. So 6 minus 2 is 4. This is 2a plus b. Okay, I kind of get stuck. That's not giving me anything. So now I'm going to say, okay, the limit of f of x as x approaches 4 from the left would have to equal the limit of f of x as x approaches 4 from the right. So I'd have to make sure there's no jump there. So from the left, here's where I'm to the left of 4. So I'd use this, a times 4 plus b. That would have to equal 4 from the right is here. X greater than 4 is 4 from the right, so that's 4 squared. So this is 4a plus b equals 16. Okay. Now I can find a and b if I have these two equations. This is where, you would solve a system of equations by lining them up. If I subtract the bottom one from the top, then I will get 2a equals 12, which means a is 6. Once I get a, I can get b by putting into either one of the two equations. So I don't know, let's say I pick this one. 2a plus b equals 4. 2 times 6 plus b equals 4. 12 plus b equals 4, which means b is a negative 8. That would be my answer. All right, that's it for day 5 and 6.